thank you. Thanks for the introduction, and thanks for inviting me. So I'll talk about joint work with my co-authors about randomness extraction problem in several different settings. So I guess okay, yeah. So I guess randomness extraction is a problem that does not require much of introduction, but I guess it's always good to review kind of the original motivation of the problem. So this problem is originally started in theoretical computer science in the 90s. So the motivation is the following. So we know that randomness is an extremely useful resource that is used in many fields in theoretical computer science, like randomized algorithm, distributed algorithm, cryptography, and so on. And often in all these models, typically we assume that perfect uniform randomness are available, and we design our algorithm or cryptographic scheme from there. So perfect uniform randomness are unbiased independent random bits, which, but in real world, the random source tend to be noisy with correlation, with bias. So this perfect uniform randomness seems to be a strong assumption, unrealistic to assume. So theoretically, it would be nice if we can rely on some weaker source of randomness or weaker type of assumptions. Randomness extraction provides a general framework to do this. So the idea is very simple. So we simply extract the uniform randomness from weaker source of random sources. And once we get the uniform bits, we are good to go. And here, a weak source is just a classical distribution of some finite domain, like n-bit string, that are correlated and biased. We don't assume any structure on it. And the only assumption we put on it is that there is some entropy that we can extract from. So this is a very nice general definition. So if we can do that, it's great. But unfortunately, it's easy to see that it's impossible to extract randomness from single such sources, even if the source has very high entropy. So there are several very beautiful notions of randomness extraction approach that get around of this impossibility result, such as CDD extractor. And this also led to a deep connection to other fields of theoretical computer science and the mathematics. And so in this talk, so I'm excited about this question. So I have been studying this question in different settings that involve quantum or non-signaling. So this talk, I will talk about this extraction approach that beyond the classical setting. And we'll actually focus on the first one, which is the quantum-proof CDD extractor. Part of the reason is that this is the newest work, so I'm excited to talk about it. Another reason is also that this seems to be the most useful notion that it has wide application in quantum cryptography. Okay, so let me start with the classical notion of CDD extractor. So the way that people get around the impossibility result is to add a short uniform seed as a catalyst for us to extract randomness from an n-bit weak source X. So we say that this extractor function is a k epsilon extractor if for every X that has k bits of entropy, the extractor's output is epsilon close to uniform. The precise notion of entropy measure and the distance measure are not so important to understand this talk, but I will comment on it later. So the general goal here is to minimize the seed length, since the seed need to be uniform. It's the most expensive resource we are using here. And also, we want to get the max out of it, so it's natural to maximize the output length. And so let me briefly mention that since the introduction of this notion, there has been many applications beyond the original motivation that pervasive in every field of theoretical computer science. It also has lots of application in cryptography and also quantum cryptography. And perhaps the most well-known application is Purvis Simplification. So let me introduce it, and as a way to motivate the notion of quantum proof randomness extractor in the quantum setting. So Purvis Simplification is also a beautiful problem studied in the 90s. So here we have Alice and Bob. They share some weak randomness, viewed as a weak key. And their goal is try to extract a uniform key through a public channel so that the key is uniform against the eavesdropper if. And so randomness extractor provides a very simple solution where the Alice simply sends a uniformly random seed Y, and then both parties just run the extractor to extract a uniform, close to uniform randomness D. And so here we need a slightly stronger notion since the if actually sees the uniform seed Y. So we require the extractor's output to be uniform even given Y. So this is called a strong extractor. And also we need the construction to be explicit. Just means that Alice and Bob can evaluate this extractor function efficiently. And actually, I think it requires more when we use this protocol as a bigger protocol, as a subprotocol in a bigger protocol. And the reason is that in this case, if we may get a chance to get the additional side information about the source X, let's call it E. And this side information could be quantum. For example, if we use this Purvis simplification as a subprotocol in QKD. So if likely it gets some quantum side information about the X. And in this case, we would require an even stronger requirement. Namely, the extractor should works against quantum side information, or the output Z should be uniform even given the seed Y and the side information E that if receive. So this leads to the notion of quantum proof strong randomness extractor. It precisely says that so it is a K epsilon quantum proof extractor if suppose that X condition E has K bits of conditional mean entropy, then the output of the extractor should be epsilon close to uniform even given Y and the side information E. And while the formal definition is not necessary, it's still nice to mention because it has very nice operational definition, and this gives a very nice operational interpretation of quantum proof randomness extractor. So this conditional mean entropy can be defined operationally through guessing probability. So this is simply log of 1 over the guessing probability, where guessing probability means the probability that if can guess X given the side information E. So mean entropy is roughly unpredictability. And the distance measure, we simply use trace distance, which also has nice operational interpretation, which is the maximal distinguishing advantage of the two states. So interpret this way, extractor is a way to distill unpredictability to indistinguishability. So if we cannot guess the source, then we cannot distinguish the output of extractor from uniform. And this operational definition is not only nice conceptually, it is also very useful to reason about this object. And in particular, this is the reason why some of the classical techniques remain hold in a quantum setting. So what do we know about this object? So classically, we know very well nowadays. So a very nice result of Goswami et al. They show that explicit construction that achieve optimal seed length, which is log in n, the source length, and the error parameter epsilon for any parameter range, for any mean entropy source k, and for any error epsilon. And it is able to extract 99% of random bit. So that's very nice. So how about the quantum notion? First, it's non-trivial. A very nice counterexample is shown by Gawansky et al. They show that a specific classical randomness extractor that is not quantum proof. So this is a non-trivial notion, but people have done a substantial work show that several existing classical constructions are actually quantum proof. However, the best construction has this length, this 10 here. You don't need to read it, but the thing is that has this quadratic dependency, log square 1 over epsilon dependency on the arrow epsilon, in compared to log of 1 over epsilon in the optimal case. And this will be theoretically interesting to close this gap. And also, if we use this in a crypto setting, which require epsilon to be negligible, this would also translate to a quadratic gap in the seed length that we need to use in the crypto scheme. So our result, we get optimal seed length for a wide range of parameters. So we show an explicit construction that gets optimal seed length for sufficiently large k. K need to be greater than roughly square root of n, and for basically any epsilon here. And we cannot extract linear fraction of it, but we can extract k to the 0.99 fraction bits out. And so the main suboptimal term is the limitation on this entropy region here. I will comment it later. And this is done by revisiting a classical framework in the 90s and show that this can be made quantum proof and improve the parameter by a new Winwin construction. Again, I'll mention this later. So let me very briefly talk about the randomness extraction framework, two other notions that I want to introduce. So the first is quantum proof multi-source extractor. So the motivating question is simple. So what if we don't have a uniform seed at all? So this is, in some sense, the original question we started from. So multi-source extractor is a notion that allows you to extract close to uniform randomness using multiple independent weak sources. So the definition is nature that if you have every source have k bits of entropy, then the output of the extractor should be close to uniform. And as a direct application, this allows you to do Purvis simplification without the perfect local randomness. So as before, we have Alice sends a seed y, but the seed is no longer uniform. It's just another weak source y. And then they both run a two-source extractor to get a uniform key z out. And as before, we would like to consider content-side information in this notion. And here, even the definition is non-trivial because now there's a multiple side information for different sources. So a natural way to think of it is that for each source, there will be some side information generated locally about the source. This E1 for X1 and ET for XT. And this side information are collected by an adversary if. So if gets all the E1 to ET and try to distinguish the output of the extractor. However, since subtle things come up, since even if the side information are generated locally, they could still share entanglement. And when it's collected by the adversary, it can break independence. And also this quantum effect of no-signaling correlation, non-local correlation, superdense coding we need to deal with. And so at the end, if you don't put any restriction, extraction may no longer be feasible. So this line of research is initiated by the work of Kaiser and Kemp, where they focus on two-source setting, and they define two nature models. So the first model is pretty-nature. So if shear correlation is harmful or entanglement is harmful, let's just make sure that E1 and E2 are independent by assumption. This could make sense in several nature settings. So they call this, so let me refer to it as independent adversary model, IA model. But they say that actually we can still deal with entanglement as long as the size of this side information, E1 and E2, are small. They are small in qubits. And they show that a specific classical extractor of this EL are quantum proof against this two-side information model. So what we do here is to generalize what we know before. So first we show a general entangled model. Let's more general site information model that unify both IA and the BS model. And this allows entanglement as bounded storage model, but without any size restriction. And the key idea here is a new way to measure the entropy, which get around certain interference issue that encountered in the bounded storage model. And that's also the reason we are able to unify the two models. And then we went one step further to develop some technique to prove GE security. And we show that essentially almost all classical two-source and multi-source extractor are either already quantum-proof in the GE model or can be transformed in a generic way to get in a semi-generic way to get a quantum-proof version with roughly the same parameter. And the only exception is the recent improved two-source extractor by Lee based on the recent breakthrough by Lerkerman and his student. Okay, so let me briefly mention the third one, physical randomness extractor. So the motivating question is the following. So what if we are paranoid about the independence assumption? So independence assumption, we usually take it for granted. But if you think about it, it's some assumption that you cannot verify. And we also don't seem to know any way to guarantee independence. So it would be nice if we can get rid of this independence assumption. And the device-independent approach gives us a viable way to do so. Because in this device-independent framework, this extractor gets a bunch of untrusted devices as a resource, extra resource to help randomness extraction. So very briefly, previous work about randomness expansion can be viewed as a seeded setting. So it still requires uniform seed and independence. And the randomness amplification line of work focuses on physics motivation. So they model this source, weak source, as a Centaur-Vajrani source, which is structured and has high mean entropy. So from this randomness extraction view, it would be nice if we can say that randomness extraction remains feasible without any independence and structural assumption. And so we call this a physical randomness extractor to stress that we are extracting randomness from a physical system with a source X and a bunch of untrusted devices. And we show a quantum secure protocol that only requires a constant bit of mean entropy from the source. So this is kind of a minimal assumption you can hope for. And in the ongoing work, we show a stronger security notion called the no signal insecure notion. This is motivated by the original physics interpretation, which I'll skip here. So in the rest of time, like 10 minutes, I would like to give a high-level kind of overview about our explicit construction of quantum-proof seeded extractor. I'll do it in a very, very high level to just give you a sense of how the construction looks like and why it will work. So this is the block sampling and extraction framework from the 90s. And it proceeds as follows. So first, you do some block sampling one by one. So what you do is that you sample your source, first block, which is the longest one, and you sample from the remaining of the source a second block, and then a third block. And here, the property you want to preserve is that you want to preserve entropy rate in each block. So the original source has entropy rate mu. Each block would also have entropy rate roughly mu. And so what do we gain from here? So we gain this block structure. And how does this block structure help us? So this allows us to do so-called block extraction as follows. So we take a very short seed. This seed only need to be able to extract from the last block, which is the shortest one. And it will extract some output. Now we can use these two seeds together as a longer seed to extract the second block, second to the last block, and get the longer seed, and then continue in this way to extract a longer seed for the next block. And at the end, we can output all of them as our output. And it can be sure that this works, the output will be uniform. So the benefit is that the seed length we actually need to pay is only the seed to extract the last block, which can be really short. And notice that this block size can grow in exponential rate since we get the exponential increase in the seed available. So we only need a logarithmic block in total. And it turns out that all the seed we need is actually used to sample this block. And to sample each block, we need log n bits. So in total, we get log square n bits of seed. This is not optimal. I'll improve it later. But this is the first idea. So let's see how this idea can give you in terms of output length, how many bits you can extract from this idea. So let's go back to the time where the first block is sampled. So we said that we can preserve the rate of the block. So this block has entropy, so it's good. However, for the next block to have entropy, we need to make sure that the residual source still has entropy. And the only tool we know is by chain rule. So we can only guarantee that the residual source has k minus the length of the blue block. And this would imply that the total sampled block length need to be less than k, or less than order k. And since we are only able to extract from this sampled block, the entropy inside the block is only mu k. And so the output length must be restricted to uk. And this is achievable. So this already put a limitation because if k is less than square root of n, then mu k is less than 1, then this is not useful at all. So what we have done is that we get an extractor that has seed length log square n and output length mu k. And then there's a second idea of self-composition that you can run this procedure recursively. And I won't get into the detail, but let me tell you how it does. So it will give you a second extractor where the seed length can be, one of the logs in the seed length can be shrunk from log to log. And if you compose it one more time, then it will become log, and so on. So if you compose it enough of time, you can eventually kill this log, and you can get a seed length of order log n. However, the output length you pay in the output length. So the output length will also shrink from mu k to mu to the s to the k times k, where s is the number of time you compose. And for this to be greater than 1 to be meaningful, you get a restriction that you need to start with a source with higher enough entropy, n to the 1 minus little o of 1, pretty high. So we improve this classical construction from the 90s using a Winwin argument. So Winwin argument is not new. It has been used in earlier construction of the extractors, but we use it in a new way because in the quantum setting we have much limited tool. But anyway, let me tell you how it works. So recall that we said the main restriction is that we can only sample the block with size less than k in order to guarantee entropy. However, let's do it, forget about this restriction. Let's just sample a long block. And along the way, we just simply assume that the residual source has 1% of entropy left, 0.01 k. This assumption may not be true, but nevertheless, let's do it. And let's extract the block and do block extraction. And we get a first candidate output W1. So this may not be true. I mean, this may not be uniform since the block source may not have entropy. But if the sampling procedure fails, that means that at some point the residual source has entropy below 1%. Then where can this entropy go? That must go to the sampled block. So it means that this block would still has 99% of entropy, 0.99 k. But this block has a length shrink by a large factor. So we can view this as a condensed weak source, and we can run through this procedure again, sample a good fraction of block from the source, and do the extraction, and assume that it doesn't work, it gives you another condensed source, and you do it once again until the source is condensed enough to get a high entropy rate. Then you can use the earlier easy version, the non-Winwin version, to extract the final output. Now you get a few candidates. You don't know which one is uniform. But you can just put it together. You know one of them is uniform. So the entropy rate is actually a quarter in this example. It's pretty high. So you do this non-win-win simple construction again, then you get the final output. So this is the high-level idea. So I'm running out of time, so I will just mention that it's kind of complicated to set up the parameter, but you can set the parameter right to control the shrinking factor and the residual entropy rate factor, and at the end you can get output alpha. This is alpha times gamma k, and this can be much larger than mu k. In particular, this k can go much below square root of n, can go much below n to the 1 minus little of 1, and can be as small as n to the 0.1. So to summarize, you can apply this self-composition idea again on top of this win-win idea, and at the end you get our extractor. I want to mention that the reason for this square root of n limitation is actually come from this quantum sampling lemma by Koenig and Renner. It's a very nice work, but it has an extra parameter loss term that does not appear in the classical setting. And so that this quantum sampling lemma stop working for k less than square root of n. Otherwise, this procedure can go and allow you to extract from n to the alpha for any constant alpha. So this gives a very natural motivation to improve the quantum sampling lemma by Koenig and Renner, which will give a better seeded extractor immediately. So at the end, I want to briefly mention a few open questions. So the first is Purvis Simplification. So it's an old question, and in the classical setting, it's studied more extensively. In particular, people also consider main in the middle attack, which is a very natural attack where this if is main in the middle that can modify, insert, and delete the message. So in particular, if we run the earlier protocol, then if can intercept this y and change it to something different, y prime. And then the extraction would fail. They would not agree on the same key. And this is a very well-studied problem classically. There's lots of beautiful work. However, if you consider the side information to be quantum, then this question remains open. And the classical solution has connection to something called a non-mutable extractor, which is a generalization of extractor. And this motivated the study of quantum-proof version of the primitive. And another thing I want to talk about is this cryptography with imperfect randomness. Since I'm running out of time, I'll just mention that this question in the multi-party setting is related to something called the network extractor. And this also motivated the study of quantum-proof network extractor in presence of quantum-side information. And finally, I think a general line of research here is that we think there's a significant gap in our understanding for crypto in a setting with classical side information and in a setting with quantum side information. And we have seen many, many examples in this talk, and certainly this come up all over the place, such as leakage resilient crypto and more. And given this recent development in excitement in quantum technology, I think it's time for our theorists to develop theory to bridge the gap. And so I'll end the talk here.
Thanks for this very nice talk. Questions for Kaimin? Yes?
You said that you will not talk about physics part of randomness, but maybe now it's the time.
Yeah, sure. So, okay, let me go back to. Okay, here. Yeah, so let me see. So let me motivate the kind of the motivation initiated in the randomness amplification work by Kobeck Renner, and later also formalized by Gallego Ileo. So there the question is that, so whether in our physical world, this randomness can be amplified. So if there is something that's uncertain, whether you can turn it into something that is totally unpredictable. And so the way kind of they formalize this question is to model this uncertainty as a center-based general source, which assumes that given any history, the next bit is still some weakly uncertain. And so this naturally gives you a center-based general source. But this is in some sense still some strong assumption. In particular, maybe we have uncertainty, but uncertainty does not need to be binary. The uncertainty may have a larger alphabet output. And so this will give you a block version of center-based general source. And the current technique developed for randomness simplification, it's not clear whether it handles this case or not. So what do we do here? In contrast, we give a protocol that works as long as this source X has sufficient amount of entropy. It does not need to be center-based generally. It does not even need to be block center-based generally. And we show that as long as this source has sufficient entropy, and as long as when you run the protocol, these devices are not communicating, then you can certify the output or output bit in the sense that you would only accept when the device is honest and the output is guaranteed to be uniform. So this translates to physics interpretation, which is a stronger notion of dichotomy theorem. So we don't need to assume that the weak unpredictability for the nature give you a center-based general source. We only need to assume that there is some unstructured way of creating enough uncertainty. And then this uncertainty can be amplified to something that is inherently unpredictable. So that's it.
Okay, thank you. Further questions? Okay, so I actually also have two questions. You say here that you only require a constant amount of min entropy.
Yeah.
So I guess this assumes that you're going to create entanglement between the devices, and usually just need this to bootstrap, or?
Yeah. So the way I view it is that this source, we are not extracting entropy from the source. We are extracting entropy from the device.
Yeah, sure. Yeah.
And this source is used to test kind of the device.
Okay.
And with a sufficient amount of uncertainty, you can. Sufficient amount of uncertainty of the source with respect to the device, you can test the device in a sound way.
Okay, and then I have a second question actually. So you mentioned in the end that like if there would be like an improved min entropy sampling result.
Yeah.
So I have a question actually. So there's another paper like after this by Omar Fawzi, Frédéric Dupuis, and actually also myself, called entanglement sampling and applications. Like, can this not be used here, or were you not aware, or?
To be honest, I haven't checked it, and I'm happy to talk offline. But
I see. Okay.
So
I see. So well, it's nice if it has applications. I was just curious whether it obviously doesn't apply, or.
Yeah, but one question I can ask is that so in this callback render, they can use any randomness efficient sampler. So this sampling does not need to use independent sample.
Okay.
So I'm wondering if your result can handle.
Yeah. So actually, we get the sampling result from an even more general theorem, from which one could also derive some other forms of sampling results if desired. But yeah, let's take that offline.
Let's take that.
More questions for Kai-Min? Yes? One more question?
Hi, Kai-Min. Thanks for the nice talk. Just have a very simple question, actually. When you mentioned about the block, how do you get sample the block to begin with? Do you also start with some randomness to do the sampling? Yeah.
Yes. So let me go to the slide. So right here. So I said that the reason that the seed length is log square n is because you also need the randomness to do sampling. And this randomness can only come from the seed. And to sample each block, you need a log n bits of entropy using randomness efficient sampler. So here we need the log and block, and you need the log square and bit of seed length to do the sampling.
Right, let's thank Kaimin again.
Thanks.